Hello everybody, my name is Fima Klebaner and I'm going to present our paper on the establishment of a mutant. My co-authors are Jeremy Baker, who is a PhD student, Pavel Chikansky, who is from Hebrew University, and Peter Jagas, who is from Chalmers in Sweden. So we are trying to model situation when a mutant appears in an established population. Our assumptions are that population 1, established population, is around its carrying capacity, which is proportional to a large number k. When a mutant appears, successful mutation appears. So we assume also that mutant's capacity, carrying capacity, is also proportional to k. So initially the picture of population sizes versus time looks like this. So you have a A1k is a large level, and population 1 undergoes random fluctuations around this level. Initially, it is at critical reproduction. And then due to competition with mutant, reproduction declines. Likewise, mutant appears with very small number of individuals, let's say 1, and has supercritical reproduction at first. And then this reproduction slowly diminishes. And we're looking at a situation when coexistence occurs, when both establish in a population. So the picture simulation of a process is here. For a time being, ignore green lines. So we have a mutant population, which is red. And you see here we have a slow, fast growth over a period of time here up to this time. And then it grows very fast, like exponentially, and forces the host population to decline, and slowly they get coexistent around some fixed equilibrium. So this is a simulation, and the purpose of the paper is to prove rigorously what we can see here. We use a model for competition as a bare bones evolution model, which is a competing binary splittings in discrete time. So the time is n. Instead of looking at the population size, we're looking at population density, which is population size relevant to k divided by k, and we denote it by vector xn k as a two-dimensional vector that represents a host population and a mutant population. And it turns out that for densities, the model becomes nonlinear dynamics F, which is a two-dimensional dynamics, plus small noise. And an important feature that this dynamic starts near an unstable fixed point. That's very important a feature of the model that results in new effects. So this is how the model can be represented. At the time n plus 1, it is just a deterministic dynamics F at point xn plus the noise of size 1 over root k. And the initial condition is when we look A1k over k and 1 over k, which is very close to the point A10. Now the point A10 is a fixed point of the dynamics F. So f of x is equal to x. And it represents resident equilibrium when there is no mutant present. So it's a saddle point. It would have been stable for the host population. Now we say when mutant establishes itself, what do we mean by that? Well, we say that mutant establishes itself when its numbers proportional to the carrying capacity, so proportional to k. So in other words, mathematically, when we have lim_inf as k goes to infinity, of the mutant density is positive. So to describe this in other results, a very important parameter is a mutant offspring mean, or twice probability of successful division at the appearance at time 0. and we denote it by rho. So because it's supercritical, the probability of successful division is bigger than half. We can say rho is bigger than 1. And we denote the constant b, 1 over log rho, as b. So one result that we obtain is that the establishment occurs exactly at times b times log k. So we show that lim x2 b log k is positive, whereas for any number r less than b, limit as k goes to infinity, x r log k converges to this fixed point, or second coordinate converges to 0. In particular, if we take any fixed n, that will be 0. It would not get established at any fixed time. You have to take time proportional to log k. And more than that, our main result is this, that if we take any number n, which could be 0, 1, 2, etc., but in general, it could be just also negative numbers. If we look at the time b log k plus n and look at the population x at the time, then as k goes to infinity, it converges to the deterministic dynamics, nth iterate of f, now at some random point, which can be expressed as h of vector 0 w. So h is some function, and w is a scalar random variable. And h is two-dimensional function, which is obtained from dynamics f. So here is a definition of h. In fact, this result is non-trivial, and main result, mathematical result of the paper, that this limit exists. So if we take this point, fixed point, it takes nth iterate of f plus x over rho into the n, and the first coordinate belongs to r, the second coordinate is positive, then we obtain that there is a limit h of x. Now what is w? W is a limit, almost sure limit, of the normed supercritical branching binary splitting of the mutant. So if we freeze the probability of division as rho over 2 at the beginning, then we obtain supercritical binary splitting, and rho minus n, yn is a martingale, and it converges. And so this is a pictures approximation of function h. This is h1, and this is h2. We do not have exact expression for h, but we know that it solves Abel equation. We know many properties of h, but we cannot solve it in closed form. And of course, existence of h is not proven. In generality, it's only for the specific function f, which appears in this model, and of course, somewhat related dynamics. Now, what is the mathematical significance of this result? Is that classical results, probably better to quote Frelin and Wenzel or Kiefer or Kurtz and Barber, they claim that effect of small noise on fixed time intervals is negligible. There is no effect. You can discard the noise. However, what we find here, that if we take intervals that go to infinity, as noise goes to 0, then the effect of small noise is sizable, and we exactly know how to describe this effect. In fact, we have initial condition. It leads to the same dynamics, deterministic dynamics as before, but now random initial condition. And random initial condition is composed from a function h obtained from dynamics f in some way, some nonlinear way, and random variable w, which is obtained by linearization of stochastic dynamics. So here, basically we say that the classical results are of course correct, but they don't tell you anything because initial point converges to the stable fixed point, converges to the fixed point, and therefore any iterate of f will result in this fixed point. So now with our result, we have as n goes to infinity, the dynamics, stochastic dynamics now converges to the correct stable fixed point of f. And so that's what we observe here. So this is a stable fixed point, x2, and this is x1, and that's a convergence of the stochastic dynamics to the deterministic dynamics. Now, one more corollary we can have from this analysis is what is the probability that mutant establishes itself. And we know from the properties of H that H of 0 is 0, and we know that extinction of the mutant and probability of limiting variable being 0 is the same, so probability W equals to 0 is exactly the extinction probability in branching processes. So the probability of establishment is 1 minus the extinction, which is 1 minus probability W equals to 0, and we can, of course, calculate it for this binary split. Now, I mentioned mathematical significance of the result. The question now, what is the biological significance of this result? And we're still thinking about that. What is the biological significance of H? What does it tell us in, what does mathematical result tell us in biological application? Now here I would like to mention a few details about the model. So here we have a bare bones models. Each population is a binary splitting, which follows this branching processes, successful probability of division, and looking at the dynamics. This is a dynamics that we obtain from this model, two-dimensional dynamics. It has 4 fixed points, total extinction, which is unstable point. We have this as a fixed point that we discussed in our analysis, is a resident equilibrium, A10, mutant equilibrium, 0, A2, and coexistence equilibrium, which is A1 minus gamma A2, A2 minus gamma A1, 1 minus gamma A squared. So gamma is a parameter which relates to how populations influence each other, interaction between populations. And of course, standing assumption that this, they're all positive, this is positive, and this is positive, and this is what we call coexistence conditions for the mutant. So finally, here is the link to our paper, and thank you very much for your attention.